So now we're on question 7, B through C. And for B, you're given the name Z2-methyl, 1-phenyl, 1-butene. So I drew that right here. Z means the two higher priority substituents are on the same side, which I've got. Good, so we're ready to go. And it's asking to predict the reagent. And the answer is actually acid catalyzed hydration. So H3O plus, whatever acid you want to put, you'll get credit, and H2O. So the reason we know this is a lot of people, okay, the first thing you do is you look to see what's added. So we're adding an OH and there's an H back here, so we're also adding an H. And we look to say, well, okay, is it added Markovnikov or anti-Markovnikov? And it's actually added Markovnikov, which might be hard to see. This is the benzylic position right here. It's one away from benzene, which is better than a tertiary position. So some people might have messed up and put hydroboration or BH3-THF as their reagent, when actually that's not true. So we know that this is Markovnikov, so we're adding an H and an OH. So we got that. It's added Markovnikov. So we got that. Now we want to look at stereoselectivity. So another way to look at this is, okay, it looks like these are added anti, but when you actually look at the stereochemistry of the original molecule, this actually wouldn't have been the case. They wouldn't have been added anti. And we can see this if, say, we used oxymercuration instead. So if we did that, because with these two checked off our list, we're between oxymerc and acid catalyzed hydration. So let's say we looked at oxymerc. So with oxymerc, you're adding an OH to the Markovnikov position, which we did, and they add anti. So OH and H are added anti to each other. Now these two, this single bond can rotate. Remember, single bonds can rotate, they have free rotation. So these two things are the same thing. I just rotated the molecule. And when we compare this to our final molecule that we're supposed to get, these are not the same thing. Here we have the methyl group on a dash, and here we have it on a wedge. So these aren't equal to each other. So we know that oxymerc does not work. So that just leaves H3O plus and H2O. So the reason why H3O plus and H2O works is because it's non-stereoselective, and in this case they would be, the H and the OH would be added syn. This is just, again, he just rotated the single bond to throw people off. So if you have a good eye, you should be able to get to this right. So the next one, this is, part C. So you're given this starting molecule in these conditions, and then on your answer sheet you're given just this template to fill in your groups. And it's asking to draw the major product with stereochemistry. And the major product is mostly one isomer. So here are reagents, Br2. This is an inert solvent, so we're going to be adding Br and Br. Bromine. Remember, those are added. We don't care about regioselectivity, Markovnikov, anti-Markovnikov, so we say who cares. And then for stereoselectivity, it's anti-only. Now this is the one where the examples in your notes where you have to make sure that, well, the more stable one is going to be the one where bromine is added anticoplanar. So here, you have to put them in the chair conformation in order to see. And here, this one would be our better chair because bromine and bromine are added axial, anti-diaxial. So that would mean on this carbon, the bromine would be pointing up. So on our sheet we would write it on a wedge, and then the other bromine on a dash since it's pointing down. This one, if you would have picked this as the right answer, you would have put this bromine on a dash and this bromine on a wedge. These are just equatorial, but this one's pointing up and this one's pointing down. But since that's not the right answer, we use this one, again, because they're at an anticoplanar and it's more stable.